This is Programme 4 of VideoTel's series on practical marine electrical knowledge. The series is made up of 8 programmes. Programme 4 deals with 3-phase cage induction motors, showing the testing of each electrical component for continuity, between-phase faults and insulation resistance testing. Then we show how to dry out a motor which has been drenched in water. This is followed by single-phase motors and motor starters used on board ship. We discuss direct online starters, star-delta starters and auto-transformer starters. There are many system variations around, so it's most important that you become familiar with the components of the electrical system and the layout of the main switchboard immediately you join a ship. Pay particular attention to the layout of the emergency switchboard. This study will pay dividends during a blackout or when troubleshooting the cause of a major breakdown. Now, we must emphasize electrical safety. The golden rule is, before any work is done on an electrical installation, first isolate the circuit by removing the supply fuses or locking the circuit breaker in the open position so that the circuit cannot be energized accidentally. Then post a warning sign to alert others that the circuit is being worked on. Then prove the circuit dead with a voltmeter or an approved line tester. A switchboard can never be considered dead unless all AC generators connected to it are stopped, locked off, and all other supplies are disconnected. These points can never be emphasized strongly enough. The most commonly used electric motors on board ships are the 3-phase squirrel cage rotor induction types with star or delta connected stator windings. These motors function in widely varying atmospheric conditions, and they are totally enclosed fan ventilated or enclosed ventilated drip proof and explosion protected types. On deck machinery, they may be in a watertight enclosure. How much maintenance and repair of motors is carried out on board ship depends on company policy. The most modern approach to maintenance relies increasingly on vibration monitoring and insulation resistance trends to determine maintenance schedules. Developing troubles are detected and remedied in time, without a motor having to be withdrawn regularly from service, as in the case of planned maintenance schedules. In addition to this, you will need to test for faults or check a motor when it's returned from shore repair. In this program, we shall demonstrate a comprehensive set of test techniques which will cover most fault-finding procedures, whatever your diagnosis of a problem may be. Some of the more common faults are overheating, failing to start, or running at low speed, an earth fault, between phase faults, and a single phasing fault. First, check that the motor shaft is free to move. Then test the terminals for being dead, even though you've isolated the supply. The test must be done between phases as well as between phases and earth. If motor heaters are fitted, isolate and test these also. Then disconnect the feeder cables so that they may be tested for continuity and insulation faults between them and between each to earth. The meter is checked first, then the test is made. You will notice that here the starter is near the motor and the ends of each feeder cable are within easy reach. If this was not the case, then first the cables would have to be tested for insulation resistance between phases to eliminate the possibility of a short circuit fault. Then one end of all 3 cables connected together would allow the testing of all 3 cables for continuity at the other ends. Having tested for continuity, the cables are checked for between-phase faults. Next, the terminal box. Each phase winding can be separately tested for between-phase faults as well as earth faults. Here, the meter reading is high, indicating a healthy insulation condition. A low reading would have indicated a faulty condition, requiring further investigation. In that case, you establish the flexible connections for each phase winding to the terminal block, after which they're marked for reference and taped together, having first been separated from the terminal block. The terminals themselves are now tested for insulation integrity between each other and between each to earth. Each time you test a part of the circuit to earth, check the insulation resistance tester first, with the probes together. Find 2 good earth points. And then test the circuit. First, the terminals to earth are checked. The phase windings have been separated electrically from all other parts of the motor. They can be tested separately to earth. We've now tested each and every separate electrical component in the circuit on the load side of the starter. These techniques, in some combination, will be used to trace an evasive fault. A typical example of insulation resistance testing occurs when a water-drenched motor is dried out. Start by testing the meter, and then find 2 good earth points. Now each phase is tested to earth. You can see that the reading indicates very low insulation. The motor needs to be dried out. Remove the rotor, taking care not to damage either the windings of the stator or the rotor cage bars or the bar connections to the common rings. By the way, the bearings will need to be checked, cleaned and repacked with grease or replaced altogether. If the motor was drenched by seawater, it must first be washed out well with fresh or distilled water to get rid of the salt. Afterwards, clean thoroughly with an approved electrical cleaning fluid to get rid of greasy deposits left after the washing. Check that the welding set is off and connect the stator windings in star according to the appropriate sketch, shown here. The windings can now be dried out by current injection from the welding set. Select a low current setting, below the load current of the motor. Turn the welding set on and check the circuit current. Note the use of a clamp meter or tongue tester instrument. Adjust to just below the full load current of the motor, carefully checking that neither the motor nor the welding set will heat up too much. This is most important. Continually check the temperature and adjust the current accordingly. Run this current injection for about 15 to 30 minutes, checking all the time the heat condition of the motor and the welding set. Switch off and recheck the insulation resistance readings to earth and between phases. Several heating cycles may be needed before the readings will rise above 1 megohm. Incidentally, whenever a motor is returned to service, always check the direction of rotation before coupling to the load. If the direction is not as required, interchange any two supply lines at the motor terminal box. This will change the direction of rotation of any three-phase motor. The motor can be re-varnished with an air drying varnish only after you obtain a steady insulation resistance reading. If you varnish too early, you may permanently seal moisture in the windings. Next, we must mention special application motors driving auxiliary deck machinery. They may be either DC motors or squirrel cage rotor induction motors of special design, allowing them to run at different speeds. Several types are used. They may be wound rotor types with external resistor control, continually changing the rotor resistance, resulting in a variation of speed. Or they may be motors of multiple pole stator construction. The control of these motors employs a series of connections by which the number of the motor's poles can be changed. For instance, a 4-pole motor can be changed to an 8-pole motor, with consequent change in speed. Where fine control of motor speed, or inching, is needed, a variable voltage Ward-Leonard control is used. This will give fine control of the speed of the motor in both directions. Now, single-phase motors. We shall deal with two kinds: commutator and capacitor start types. If a breakdown or malfunction occurs with a single-phase motor, the test procedures described in connection with the three-phase machines also apply. The design features of a single-phase motor add one or two other procedures. For instance, the centrifugal switch contacts which disconnect the motor's start winding at full speed must be checked and cleaned, and the switch mechanism checked for easy movement. First, clean the mechanism with an approved cleaner. Then apply lubricant sparingly and wipe off surplus oil. Then disconnect the starting capacitor, connected to a multimeter set to read resistance. A gradual charging of the capacitor will occur if it's in good order. Discharge the capacitor before reconnecting. The windings of all motors collect dust, grease and moisture. Carefully examine their condition, check for damaged insulation, and clean with an approved electrical cleaner. Check and clean all ventilation grooves. On a capacitor starting motor, if the direction of rotation is wrong, for instance after an overhaul, just change over the leads to the start winding, which are connected to the capacitor and the centrifugal switch. If a commutator motor is used, its commutator must be kept clean, free from carbon dust, oil and grease. Lightly clean off any carbon deposits. After checking and cleaning, replace the armature, ensuring that no damage is done to the windings. Check the brushes for length. Ensure that brushes are correctly bedded onto the commutator surface. A short brush will have insufficient spring pressure, resulting in bad contact or uneven wear on the commutator. Now let's look at starters or controls in the case of deck machinery. The most frequently used ones on board ship are direct online starters, star-delta starters, and auto-transformer starters for really heavy-duty drives. Their function is to start and stop the motor normally and provide protection against the consequences of overcurrent, undervoltage, or single-phasing conditions. This is a schematic view of a direct online starter. It's the simplest starter, comprising one contactor, an overcurrent relay with a set of push buttons, and indicator lamps. When the starter button is operated, the control circuit to the contactor coil closes three main contacts, connecting the power supply to the motor. At the same time, a normally open auxiliary contact is made, providing a retaining circuit for the contactor when the start button is released. The closing coil circuitry will now remain closed until the stop button or the overcurrent relay interrupts it. At this point, the main contacts are pulled apart by a spring in the contactor. The closing coil circuitry of the contactor is fed by a step-down transformer, providing a 110-volt supply. The contactor coil also acts as a no-volt coil protection, interrupting the circuit when a serious and prolonged voltage drop occurs. This feature prevents the motor automatically starting after a power interruption. The control circuitry has its own set of fuses. This starter needs little attention. All the components are fully enclosed and self-contained. However, they need to be kept clean and the components changed if they become defective. Periodically check terminals and contacts. An older version of the starter, shown here, will illustrate the working of each basic unit. Isolator switch, transformer, contactor coil, auxiliary contacts, main contacts, and overcurrent relays. If you do have an older type starter, the main contact points need cleaning from time to time, as shown here. This drawing shows the contactor circuitry for a star-delta starter. One starter contactor connects the motor to the supply, while another contactor connects the motor phase windings in a star formation. In this configuration, the motor takes a reduced starting current compared with direct online starting. A timer will then disengage the star contactor and close the delta contactor, connecting the motor's phase windings in delta. Ensure that the timer is set correctly in relation to rated run-up time of the motor. Here you can see the various components of the star-delta starter, with star and line contactors, and delta contactors, and timer. The protection systems described in connection with the direct online starter are the same in this one. Another way to reduce the initial starting current is utilized by an auto-transformer starter, where the supply transformer is tapped to give a reduced starting voltage. Tappings of 50%, 60%, and 70% are typical. Again, a timer will cause the motor to be connected to full line voltage after the motor has run up to speed. This system is a Korndorfer unit. After the motor has reached full speed, a timer switches the motor to direct online before the tapping contactor is released, avoiding a surge current which arises otherwise during changeover. Again, the control and protection circuitry is the same as described earlier. The controls for variable speed motors function differently in that while connecting the supply to the motor, they alter either the resistance of the rotor winding or the number of stator poles. The control unit of the multi-pole motor has several extra contact linkages which are switched in and out very frequently as the motor is switched on and off and from low speed to high speed. These contacts must be checked and cleaned frequently. Any badly burned contactors must be replaced. The Ward-Leonard control unit switches DC current in both directions as it controls the speed of the motor. Deck machines invariably include electromagnetic brakes, seen here being serviced. This concludes the subject of Programme 4. We've discussed some general points about three-phase motor maintenance. We demonstrated a number of test procedures used for fault tracing and insulation resistance testing. We saw how to dry out a drenched motor by current injection from a welding set. We demonstrated some maintenance techniques for single-phase motors and described the practical applications relating to starters. We recommend that you watch this program again and that you consult the book Practical Marine Electrical Knowledge, which accompanies this series and will allow you to study certain aspects in greater detail. Finally, here's a list of contents for all the programs in the series.